In today's episode, we deconstruct the history of roofing through the lens of materials science, from the thermal insulation of pre-colonial thatch to the metamorphic durability of slate and the petroleum chemistry of modern asphalt. We analyze the physical limitations and longevity of every layer we've ever put on our heads. Discover why wood rots, why copper turns green, and why your current roof is essentially a ticking clock of UV degradation. Stay tuned. Welcome back to Why Is That, Dad? I'm Phil, and with me today is my curious co-pilot.
I'm Annalise.
I hope you all had a blessed Christmas and a Happy New Year. We had a little rest and relaxation with the family, but with a family of 7 kids, I probably get more rest and relaxation when I go to work. Anyways, I'm excited to put out another podcast. Today, we're continuing our home building series. Today's topic is one of the most important things you'll look at when buying a home, because it's the thing that protects the rest of the house. When we got this old home earlier this year, it's the first question. Does the roof leak and how long will it last for? Today, Annalise, we aren't just answering what is a roof. We are getting into the physics of shelter, material science, structural loads, and a chronological engineering of the American roof. We're going to walk through the timeline of history, and for every era, we're going to look at the science of the material used, how long it lasted, and the physical limitations that eventually caused it to fail.
The roof. Oh, before we get started, Dad, I have a joke for you about roofs.
Sure, what you got?
Oh, never mind. It'd go way over your head. Get it?
Yeah, I get it. That's a good start.
Really, though, we have a roof. You patched a section earlier this year with those shingles, one overlapping the layer below it. Made me wonder, why do shingles have grit on it? How does roofing work to keep water out? Why don't they just put a big, huge piece of plastic up? Tarps keep water out. Why's that, Dad?
Well, the simple answer to your question, what keeps the house dry, is a combination of hydrophobicity, which is water repelling, and overlapping geometry. Most roofs are water shedding and not actually waterproof. They work because the materials are laid like fish scales. The multiple layers add redundancy to the system. If it were just a sheet of plastic, one hole and you'd have a problem. With roofing, as long as gravity pulls the water down faster than the wind pushes it up, you stay dry.
So it's a race? Gravity versus the rain?
Exactly, and that race started thousands of years ago with the simplest materials. Long before the Industrial Revolution, people used what was within walking distance. In pre-colonial America, indigenous peoples like the Wampanoags or the Haudenosaunee used bark and mats.
Wait, bark? Like off a tree?
Specifically birch bark. It's a masterpiece of natural engineering. Birch bark contains high levels of betulin, a resin that makes the bark naturally waterproof and resistant to rot. They would layer these shingles of bark over a frame. It was lightweight, portable, and scientifically sound because the resin acted as a natural chemical barrier to water. But when European settlers arrived, they brought thatch.
That's just dried grass, right? How does grass stop a thunderstorm?
It's all about packing density in the hydrophobic cuticle. You see, the outer skin of a reed or a straw stalk is naturally waxy to keep the plant's own water inside. This is a lipid-based coating that prevents evaporation from the plant. But when dead, it prevents absorption. When you bundle thousands of them together very tightly, with the cut ends facing down at a steep angle, the water doesn't soak into the stalks. It travels along the surface of them.
But does all grass last the same amount of time? When we put our grass clippings in the compost, it turns into a wet, goopy sludge pretty quickly. Even when Grandpa cuts hay, he has to store the hay before it rains so it doesn't go bad.
Yeah, not all grass. Common straw or broom sedge might rot in 10 years, especially in the humid American colonies. But there is a heavyweight champion called Phragmites, or the common water reed. These reeds grow in wetlands and have a hard shell exterior packed with silica, the same stuff used to make glass. Because they are hollow and rigid, a Phragmites roof can breathe, drying out much faster than a straw roof.
Phragmites? Aren't they really invasive?
Yes, Phragmites australis is a highly invasive plant native to Europe. There is a native Phragmites americanus that can be used, but it isn't quite as well. They don't grow as long, have thinner stems, and thus don't last as long. When the colonists came to bring their traditional roofing skills to America, Phragmites australis wasn't here, but it's worth discussing. While straw lasted 10 years, this water reed roof could last 40 to 60 years. And although they aren't popular in the States, there are hundreds of thousands of homes in Europe that still have thatched roofs.
40 to 60 years? That's incredible. I've never seen a thatched roof in America. Why is that, Dad?
Well, it had some serious drawbacks. Like I mentioned, the humidity on the East Coast decreased their longevity. Birds would use thatched material for their nests. Snakes and rodents would make their homes in them. America didn't have the preferred materials for thatch, and they were extremely labor-intensive to construct, with the average roof taking 2 to 4 weeks to complete. Compare that to the modern shingles, which can be finished in as little as a day or two.
America had a shortage of skilled labor? Sounds familiar. Well, if thatch wasn't the preferred method, what did they use?
Cedar shakes. Cedar was the king of early American roofing. Here's what's great about cedar shakes. Wood is hygroscopic. This means it absorbs and releases moisture. When it rains, the wood cells swell, causing the shingles to press tightly against each other, creating a tighter seal. When the sun comes out, they shrink, allowing the roof to breathe and dry out the attic. Cedar also contains thuhaplicins. Thujaplicins? Thuhaplicins? I should know how to pronounce that. Thujaplicins. Natural oils that are toxic to fungi, so they naturally prevent rot. A good cedar roof lasts 30 to 40 years.
That's a long time for a piece of wood. But if they lasted so long, why don't we see them as much anymore?
Actually, there are still about 1 million homes in the U.S. that have cedar shake roofs, but they aren't nearly as common as they used to be for a number of reasons. First, let's talk about what happens to them over time. UV degradation and warping. Over decades, the sun breaks down the lignin. That's the glue that holds the wood fibers together. The shingles start to cup or curl at the edges. Once they curl, they create a ramp for the wind to blow right underneath them.
Is that why people stopped using them?
No, it was due to something worse than a leaky roof. What else are thin, oily shims of wood good for?
Fire?
Exactly. Cedar shakes are extremely flammable. One historical anecdote I have shows this well. In the mid-19th century, American cities like Boston became obsessed with a mansard roof, a trendy French architectural style characterized by 4 steep, nearly vertical sides. While they looked elegant, these roofs were essentially a massive legal loophole. They allowed homeowners to squeeze an entire extra floor of living space into their house without technically increasing the building's height for tax purposes. To keep these tax dodge additions lightweight, they were built with intricate timber skeletons and covered in thousands of dry, overlapping cedar or pine shingles. This created a citywide attic forest of highly flammable organic materials sitting high above the reach of early firefighting equipment. The structural flaw of the mansard roof turned into a catastrophe during the Great Boston Fire of 1872. When the blaze began in a basement, the heat rose rapidly, turning the wood-shingled rooftops into a series of elevated fuel tanks. Because wood has a relatively low flash point, the roofs ignited before the flames even reached the lower floors, allowing the fire to leap from building to building across narrow streets as wind-blown embers, or brands, landed on parched cedar. The devastation was so absolute that insurance companies and city planners finally revolted, mandating a transition to Class A fire-retardant materials like slate and terracotta, effectively ending the era of the wooden urban hat in favor of the Stone Age of roofing.
A stone roof? Oh, they have one of those at St. Patrick's Cathedral where we go to choir.
Good observation. By the 1800s, American cities were tired of burning down. They began passing laws requiring fireproof roofs. Enter slate. Slate is a metamorphic rock. It started as mud at the bottom of an ocean millions of years ago, and then heat and pressure squeezed it into layers. The science here is called foliation. Because of its molecular structure, slate has cleavage planes. You can tap it with a chisel, and it splits into perfectly flat, thin sheets. And it lasts a long time. This is the forever roof. A slate roof can last 100 to 200 years. There are slate roofs in Europe that have been there since the 1600s.
200 years? Why doesn't everyone have one?
Two words, dead load. In engineering, dead load is a constant weight of the building materials. A standard asphalt roof weighs about 200 pounds per square, a square being a 10 foot by 10 foot area. Slate weighs 800 to 1,500 pounds per square. If you put a slate roof on a house built for shingles, the weight of the stone would literally crush the walls or snap the rafters. To have a slate roof, you have to build the entire house like a fortress. It's also brittle. It has high compressive strength, but low tensile strength. If a heavy branch falls on it, it shatters like a dinner plate.
What about those red, curvy roofs, like the ones in the desert?
That's clay tile. The science here is ceramics. Clay is molded and then fired in a kiln at 1,000 degrees Celsius. This triggers a chemical process called sintering, where the particles fuse into a glass-like waterproof solid. The half-pipe shape of a clay tile isn't just for looks, though. It creates an air gap between the tile and the roof deck. This is a thermal break. In hot climates, the sun heats the tile, but that heat is carried away by the air flowing under the tile before it can get into your bedroom. This also lasted a long time, anywhere from 50 to 100 years. But, like everything else, it had its limitations. Clay is slightly porous. If water gets into a microscopic pore in the clay and then freezes, the water expands by 9%. That expansion pressure can reach 30,000 pounds per square inch, enough to shatter the tile from the inside out. That's why you rarely see clay tiles in places with snowy winters. Other reason terracotta isn't seen everywhere is because it is also heavy, just like the slate.
So if wood was a fire hazard and slate was a house crusher, what did the average person do in the middle?
Well, we entered the tin age. From about 1850 to 1920, tin plate and turna plate, which is steel dipped in lead tin alloy, became the most common roofing materials in American cities. And I should say, a tin plate is a steel plate covered in tin. So tin was a perfect middle ground. It was fireproof like stone, but light enough that you didn't need to reinforce the walls. It was sold in small sheets that were soldered together. Because the people still loved the look of slate, many manufacturers started making embossed tin shingles. These were metal squares stamped with patterns to mimic the texture of slate. They didn't last as long, though, only 40 to 50 years, if you painted it. If you didn't paint it, the steel under the tin would oxidize and rust.
Oh, an early precursor to modern metal roofs. The more things change, the more they stay the same.
True, that's ironic. One metal that probably won't become popular again because of its expense is copper, though. These lasted quite a while, 70 to 100 years. Most of the metal-inspired roofs were made of steel. They fail because of oxidation, rust. When iron oxidizes, the rust is flaky and falls off, exposing new metal to be eaten away until the metal is gone. But when copper oxidizes, it creates what they call a patina.
Like the Statue of Liberty, green, the color of boogers. Ha ha!
Maybe boogers when you're sick. That's some gross boogers. Anyways, that green layer is a chemical called copper carbonate. Unlike rust, the patina is adherent. It sticks to the metal and forms a microscopic airtight seal. It's like the copper grows its own suit of armor. Once it turns green, the oxidation practically stops.
That's really cool. What about the other metal roofs that don't rust? Grandpa's barn roof is made of metal and it's green, but I know it's not copper.
That's likely galvanized steel or aluminum. Steel would rust in a week if we didn't protect it, so we use galvanization. We coat the steel in zinc. Zinc is a sacrificial metal. On the galvanic scale, zinc is less noble than steel, meaning it will corrode first. If the roof gets scratched, the zinc nearby will actually chemically react to protect the exposed steel. It's like a bodyguard taking a hit for the king. Then the roof is painted green because it's coated in an advanced polymer that is designed to protect the steel underneath it. But even this has some drawbacks. First, we have thermal expansion. Metal has a high coefficient of expansion. A 40-foot panel of metal can grow by an inch in the summer sun. If you nail it down too tight, the metal will actually oil can or buckle or rip the nails out. And then we have acoustics. Without heavy insulation, metal lacks the mass to dampen sound. The kinetic energy of a raindrop is transferred directly into the metal, causing it to vibrate like a drum.
So metal is loud and moves around. Is that why we end up with the sandpaper tiles?
Welcome to the 20th century. This is what is on 80% of American homes. It's the asphalt shingle. Asphalt, or bitumen, is a viscoelastic polymer. That's a fancy way of saying it's a liquid that acts like a solid. It's a byproduct of oil refining. To make a shingle, we take a mat made of fiberglass, essentially tiny threads of glass, and soak it in hot asphalt. Then we press crushed stone granules into the top. This only lasts 15 to 30 years though.
Wait, that's an average of 20 years? That's the shortest one yet. Why did we pick the one that breaks the fastest?
Because it's cheap and easy to install. It's the fast fashion of roofing, but the physics of its failure is really interesting. The enemy of the asphalt shingle is UV radiation and volatiles. Inside the asphalt are maltines, oily molecules that keep the shingle flexible. The sun's UV rays are high energy. They act like tiny molecular scissors, snipping the chemical bonds of the maltines. As those oils disappear, the shingle becomes brittle.
Is that why the little rocks are there? To block the sun?
Precisely. The granules are sacrificial UV shields. Once those rocks wash off into the gutters, the sun hits the black asphalt directly, and the shingle bakes until it cracks. This is called alligatoring because the cracks look like reptile skin. Also, thermal shock. On a July day, the roof is about 160 degrees Fahrenheit. A sudden rainstorm drops it to 70 degrees Fahrenheit in seconds. The rapid contraction causes microscopic tears. Do that every day for 20 years, and the shield eventually shatters.
And to think the grit was just only for good grip when walking on it. So our roof is just a giant oil-soaked cracker that's slowly drying out.
That's a terrifyingly accurate description, but yes.
Well, one more question. Not entirely the same as the roof, but related. Okay, so the roof sheds the water, but then it goes into the gutters. Did we always have gutters? I can't imagine gutters being used on thatch roofs.
You're right, we didn't always have gutters, but we still needed a way of handling water. Before we had the modern aluminum channels we see today, the world relied on the science of the throw. For centuries, the primary defense against water was the deep eave, a roof that extended several feet beyond the walls. By using a steep pitch, architects ensured that rain gained enough kinetic energy to literally jump away from the building's foundation. However, this created a drip line, a physical trench carved into the earth by the constant hammering of water. To protect the base of the house from splashback, which carries moisture and rot-inducing minerals, builders installed plinths, thickened stone bases, or splash blocks, to break the water's energy and divert it into the French drains, which were underground trenches filled with loose rubble to provide a path of least resistance for the runoff. As architecture became more vertical and crowded, especially in Gothic Europe, simply throwing water off the side was no longer an option. Builders began carving stone channels into the roof's edge, leading to the invention of the gargoyle. Derived from the French word gargoule, meaning throat, these stone monsters were the world's first external downspouts. They were engineered as long, horizontal projectiles that used gravity-fed pressures to shoot water 6 to 10 feet away from the walls. This protected the delicate mortar and stained glass from erosion. Eventually, these stone spouts were replaced by heavy cast iron and lead troughs during the Industrial Revolution, though they still suffer from the seam problem, where the joints will leak due to the constant expansion and contraction of the different metals. The final leap in gutter history happened in the 1960s, with the invention of the seamless aluminum gutter machine by Art Knudsen. Before this, gutters were sold in 10-foot sections that had to be soldered together, creating a weak point at every joint. Knudsen's machine allowed a contractor to bring a giant coil of flat aluminum to a house and roll form a single, continuous channel that could be 50 or 100 feet long. This manufacturing breakthrough utilized the science of the curve, where the metal is folded into a K-style profile to increase its structural rigidity. Today, we combine this with the Coanda effect in our downspouts.
The Coanda effect?
In the context of your gutters, the Coanda effect is a tendency of a fluid, like rainwater, to stay stuck to a curved surface rather than falling straight down. You've probably seen this before. Because water molecules are attracted to the surface of your downspout, a property called adhesion, which we've talked about in a previous episode, The water hugs the interior walls of the pipe as it rounds a curve or an elbow. Instead of dropping through the center of the pipe and crashing into the bottom with a loud plink, the water slides down the sides. This uses friction against the pipe walls to slow the water's velocity and makes the drainage much quieter.
They've got funny names for all sorts of scientific ideas.
Yeah, sounds like a future podcast idea.
Back to the shingles, though. Dad, if we know asphalt shingles don't last long and are made of oil, why don't we change?
We're starting to. The asphalt era had a huge impact on our environment. We tear off 11 million tons of shingles a year in the U.S. They sit in landfills forever because they're essentially rocks glued together with oil. But ultimately, people use what's effective and what is cost competitive, and that's asphalt shingles. When something is cheaper or more effective or provides additional utility comes along, maybe we'll switch to that. And that's what we're seeing in the future. Our roofs will become power plants. We're seeing the rise of photovoltaic shingles. Instead of just a shield, the roof became a harvester. We're moving from the passive era to the active era. Culturally, the roof has always been a symbol of home. In many languages, the word for a roof is a metaphor for the whole house. When we say a roof over your head, we mean safety. Whether it's grass, stone, metal, or oil, the goal is the same, creating a dry space for humans to dream.
So, why should I care about all this material stuff?
Because one day, you'll be the one choosing the shield. Knowing the science means you aren't just buying sandpaper. You're understanding how to fight the specific climate you live in. If you live where it's hot, you want the science of the curve and the clay terracotta tiles. If you live where it's snowy, you want the metal age so the snow slides off before it gets too heavy. Understanding your house makes you a better inhabitant of the world. It turns a thing into a system.
I think I'll just build a house out of the forever stone and never worry about it again.
A wise choice. Just make sure the walls are thick. Before we climb down from the roof, let's see if our listeners were paying attention to the physics. Annalise?
Trivia time! Question 1. We talked about wood shingles being hygroscopic. What does that mean they do when it rains? Question 2. Why is a slate roof called a forever roof? And what is the dead load problem that makes it hard to use? Question 3. What is the Coanda effect in our gutters? If you know the answers, yell them out loud so we can hear you, even if you're out in public. The listeners who got last episode's questions correct are my Aunt Kiara. Hey, someone needs to answer these questions. They won't answer themselves.
If you know the answers, tell a friend. If you enjoyed this deep dive into the canopy of our homes, please consider leaving us a 5-star review on your podcast app. It helps other curious families find us.
And check out our YouTube channel, Contemplative Chaos.
Thanks for listening. Stay curious and stay dry. God bless.
Bye!